All right. Hi, everyone. Good morning. Welcome to Lecture 6. In this lecture, we're going to be talking about one algorithm for processing the data in a graph. And then afterwards, I'm going to be talking about the internal representation of graphs inside of our computers so as to know what are the implications of the different ways in which we can store a graph inside of the computer. Okay, let's get started. All right, so if you have a look at this graph, which node do you think is more important, 0 or 1? Yes. Oh, sure, yeah. Is it better now? Yeah. 0 because we have two disconnected. Right. Okay. Okay, so this is a directed graph. So if we had an undirected graph, in that case, what would you say? For example, 0 or let's say 3. So what is the first thing that comes to mind when it comes to assessing the significance of each node? What is it that you can see that kind of tells you, okay, this node is kind of more important? The first idea. Pardon me? Yes, degree, right. So the first thing that I'm saying that there are like 5 edges connected to the node 0, but for example, only 3 edges connected to node 3. So I might say, okay, that's probably we can say that node 0 is more important. Okay, so let's bring this idea to something like a social network or maybe websites on the internet. So in the context of social networks, if I have a Twitter account and then 100 people follow me, another person has a Twitter account, another 100 people follow that person. So in that case, both of us have the same degree, right? My account could be represented with a node, the other person too. So the degrees are the same. Can we say that the importance of these two nodes are the same in that social network graph? Or okay, let me make it more extreme. If I have 1,000 followers and that other person has only 100 followers, can I say that my account has more influence on that social network? Pardon me? No, just let's assume that there is no weight. Yes, that's a great point. So it's not only that the number of followers matters, it's also important who those followers are. Because if we have 100 very important people who have a lot of followers themselves, then that would be that 100 followers would be more important than my 1,000 followers, which might be like people having a couple of followers themselves. So this idea brings us to the fact that in order to assess the importance or influence of a node in a graph, just looking at the degree or the number of edges connected to a node cannot be really very helpful, a very helpful measure. It doesn't mean that it's not helpful at all, because it carries some part of that importance, but it's not the entire story. Okay, so now if we move on to, okay, this question in general is called the centrality problem. So we have a lot of measures in order to basically analyze a graph and measure the importance or significance of different nodes. And you can take a look at this link when you have time. We have a lot of, there's like a million things you can compute about a graph, and a lot of it deals with this idea of centrality. For example, we have this concept of betweenness in a graph. So there is a measure that computes when you pass information between two nodes, for each node, what is the fraction of the time that information has to pass through this particular node. So it means that if a node has a high betweenness number, so any two people on that graph that communicate, that information has to pass through that kind of central node. So it's a very helpful measure. Or we have other measures like, for example, closeness, and yeah, a lot of other measures. So here we just looked at the degree centrality, the number of edges connected to each node, which is not that much helpful all the time, especially in social networks. Then here we're going to look at an algorithm called PageRank, which is the algorithm that actually made Google very famous, because this is basically the idea behind their search algorithm. So PageRank there's the same kind of similar idea behind PageRank. So if I have a web page, and let's say 1,000 other web pages link to my page, and then there's another web page that only 5 other pages link to, then it doesn't necessarily mean that my web page is more important, because those 1,000 links could be coming from like anonymous websites that don't have a lot of people linking to them themselves. So in that case, we want to have some kind of a measure that could tell us how important those linkers are. So for this is what Google used, and at least in the early days. Right now, they probably have advanced it by like a ton, but this is kind of the general idea behind it. So let's take a look at a simplified version of this PageRank and see if we can gain more insight into this particular graph that we have here, the importance of each node. Okay. So in the code that I have here, we have a stimulated web surfer. Okay, we start at some random node in the graph, and then with probability alpha, then that random web surfer chooses a completely random node in the network. So suppose that is a website, that node is a particular website that the web surfer is at right now. And then there's a probability of alpha that person just goes to an entirely random web page on the internet. And with probability 1 minus alpha, then that user chooses a random neighbor of the current node, meaning that that person uses a link inside of that page to go to another web page. Okay. And then we repeat this step over and over again to basically construct like something like a random walk, and then analyze the results to find out what are the nodes that are visited most often. Okay, so let's take a look at the code. We take in the graph, and then alpha is the probability that we just defined. Okay, and we do 100,000 iterations. So the code should be fairly readable. Okay, I have a visited dictionary. It's a counter dictionary, meaning that if I start adding items to it, then the number of counts are going to be defined by default. And then here we have the nodes of that graph, and okay, we define a current node, just randomly pick one of the nodes in the network. Okay. Then we do 100,000 iterations here inside this block. So what we do is that we generate a random number between 0 and 1, okay? If alpha is greater than that number, it means that that user is clicking on a link in that page. Otherwise, it means that, if it's smaller than alpha, it means that that user is choosing a completely random node on the graph, completely random web page on the internet. However, if it's greater than alpha, then it means that that person is clicking on a link in that web page. This is why here, I just randomly pick the next node, just in the entire graph. However, here, I choose between one of the neighbors. So that's the only difference between these two lines of code. This is a completely random web page represented on that graph. However, this is one of the neighbors of the current node. Okay. Then I increase the count of the number of times that we have visited that particular node by 1, and then repeat the whole process again. So you can you can see that this is dependent on the connections in the network, because here at this step, I'm choosing the next node as one of the neighbors of the current node. Okay, so let's run the simulation. All right. Okay, now because I have defined this visited as a counter, there is this method that comes with it, a convenient method called most common, which basically just gives us the most common counts in that counter object. Okay, so here we can see that, you guessed it right, node 0 was very important. So we can see that there is some correlation between the number of edges connected to a node and also the importance of it in terms of the PageRank algorithm. And you can also see that it has ranked node 2 above node 1. So let's take a look at the graph again. So 0, 2, 1. Okay, 0, 2, 1. These are the most important ones. Here, for example, okay, why do you think node 2 is above node 4 in this case? So this PageRank is telling us that 2 is more important than 4. Yes? Exactly, exactly. So for node 4, no information can propagate from this part of the graph over to this part of the graph, because it only goes from 4 to 0. However, for 2, for example, we have this bidirectionality, we have this other edge, so information can flow more easily using that node 2 compared to node 4. Okay, let me bring back the code. So any questions about the code here and the algorithm in general? Okay. All right. Okay, so the conclusion is that a link from a popular web page is more valuable than a link from a no-name page with no one linking to that page, basically. So if you have a link to your page on a famous news website or on one of the most important Wikipedia pages, that's much more important than probably tens of thousands of anonymous people linking to your page, because that one link, that one or two links are much more important. Okay, so this algorithm kind of, the idea here is used to sort the pages by number of incoming links, and this is, again, what Google used to use in the early days. However, note that Google combines the information from your search keywords with this information. Otherwise, it would have shown the same similar search results every time. So that wouldn't make sense. Okay, so here I'm just printing the number of incoming links, and you can see that just based on that value, yes, node 0 still ranks first, but for example, it ranks node 4 above node 2 because there is this thing about the direction of the edges, and basically we can see that it's not that accurate compared to this one. This one here makes a lot more sense, at least intuitively. Okay. All right, one other thing to note that is, okay, what is one problem with this algorithm? If we are Google and we want to implement that for websites on the internet, what would be a problem that we run into pretty quickly? So we want to rank web pages based on this simulation that we're doing. Yes? Mm-hmm. But it takes, takes that into account, right? So by running this in... Oh yeah, there's a lot of other information that we have to take into account, but before getting to that point, that's, I mean, further down the road, even before that. You have the code, you want to go ahead and implement it, like take half of the internet and rank the web pages according to this algorithm. What is the problem with that? Yeah, sure, that could be a problem as well. Sure, there's a more fundamental problem. In terms of practicality, yes? Yeah, there you go, exactly. So there's no way to possibly use this algorithm for the entire internet or even a fraction of the internet, because running this simulation is very, very costly. So in reality, the beauty of this PageRank algorithm is that there is an analytical solution to it using linear algebra that works out very nicely. You don't have to run a simulation to compute those ranks, but we're not going to go into that detail here. So that's what makes it a really useful algorithm. Okay. So there are, again, a bunch of other graph properties that you can take a look at. This is obviously not going to be on a quiz or something, but just a couple of useful links. Okay, so a lot of these concepts are coming from mathematics. Graphs are basically just a topic of mathematics, and you can imagine how many things mathematicians have discovered about them over the many years that we have had graphs. But a lot of these concepts also have practical importance as well. Okay, so let me see. Okay, so for the next, okay, so before that, just to make you more motivated to this topic of graphs, last year in MDS we had a capstone project. There was a company that was interested in having image recognition kind of algorithm that they wanted to use that for detecting 3D objects. Instead of looking at a 2D image, they had like this sensors that could capture basically what's called a point cloud. So instead of having a 2D image with colors and stuff, there's just a representation, for example, of this desk over here as just points in the 3D space. And they were able to capture that kind of information. So for example, they wanted to look at like a street or something and detect like cars or bicycles and things like that. This is something like I think Tesla cars also do. They detect other cars, bicycles, and pedestrians, stuff like that. And they wanted some kind of an algorithm that would do this. And in that case, that whole structure could be represented as a connected graph, basically. So we used that inside of a machine learning model, and it worked pretty nicely. So you can imagine that if we had represented that thing just as a 3D matrix, the whole algorithm could have become much more inefficient. And we will learn why that's the case in the next section. So just the motivation there. And maybe something else here to this, just to give you an example of how this could be important. Let me see. Okay. All right. So there is an interesting type of analysis that you can do. It's called a Gaussian graphical model. And, okay. So, take a look at this. So a friend of mine and I started working on a project that was interested in the relationship between different psychological disorders. So we had like a large data set containing like thousands of people, and in each column of that data set we had scores for questionnaires that would measure, for example, how anxious a person is, what is the state of their sleep quality and stuff like that. And then you can basically represent those variables on a graph And then through some kind of algorithm, you can compute the weights on those graphs, which is just the strength of the correlation between those variables. And it's actually very nice to see that, for example, if you run that centrality measure kind of thing, you would see that something like what we found was that fear of lack of control over your life is one of the most important central features on this psychological disorder graph. So it kind of plays a very important role rather than sleep quality, for example. And again, this is just an application of how you can apply these concepts and make real practical sense of it for a problem over here that will be very valuable for perhaps medical or psychotherapical purposes. Yeah, just a nice example here to give you maybe more motivation. Okay. All right. So, graph representations. So, any questions before moving on to the other section? Okay. Okay, so suppose that we have a graph like this over here, and the way that we can represent this graph in our computer is by making what's called an adjacency list. So what's an adjacency list? It would look something similar to this. Not exactly, but here's just a list of the edges that we have. This is one particular way that we can store this graph inside of our computer, right? So 0 to 1, 0 to 2, 1 to 2, so on and so forth. Okay, so what would be a problem with this particular representation? Yes? There could be directionality if you want. So for example, if you have 0 and 1, if you also have 1 and 0, that means that, okay, it's bidirectional, or if you just have one of those, it means that it goes from one direction to the other. So yeah, you could represent both of these cases. Yes? Yeah, again, the kind of problem we keep going back to. So if you want to find if two nodes are connected, you have to basically search through this thing. Okay, so that's one downside. It doesn't mean that this is a fundamentally bad way of representing this graph. It's just one way, and it has its own downside. Okay, there's another way of representing a graph, and that's called instead of saying an adjacency list, it's called an adjacency matrix. And let's see what it looks like. Okay, so each row and each column of this matrix corresponds to one of the nodes of the graph, and what you see here on the matrix is whether or not two nodes are connected. So for example, if I can, let me draw the graph again, put it side by side. Yeah, I have to zoom out, sorry. Okay, for example, node 0 is connected to 1 and to 2, and here on this matrix you can see that, okay, this row represents node 0, and then the columns represent other nodes. So it's connected to 1 and 2, and here we see a value of 1 for index 1 and for index 2. So basically saying that, okay, this node is connected to these two other nodes. What would be, okay, so if you have a 1 here on the diagonal, what does that mean? Yes, it means that we have a self loop, so the node linking to itself. Okay. So, any questions about this particular representation? Just to make sure that we're on the same page. Okay. So the benefit of this is that if we know the identifier for that particular node, we can directly go and look at the information for that node. For example, here, if we had something like this, yeah, it doesn't work here. Let's add 2, let's say 1. We can directly query that particular edge, for example, or query a particular row in that case. So for example, here, the first row contains information about the first node. Okay. All right, one other question. Why is this matrix symmetric? Right, because it's an undirected graph, it means that if node 0 is connected to 1, 1 is also connected to 0, so it would be symmetric. But if it's a directional graph, we can imagine that we can have different values on the different sides of the matrix. Yes? Yeah, I know that it's something that you'd encounter with Markov models that you're going to learn in 575. I don't remember the exact details why that happens right now, but I know that's coming up. Yep. Okay. All right. Okay. So, in what situation would we have numbers other than 1 on that adjacency matrix? Yes, sure, exactly. If the graph was weighted, we could easily represent those weights on this adjacency matrix. Okay, let's move on. All right. Okay, so the performance implication is that looking up a particular edge using the adjacency matrix takes O of 1 time, constant in time. This is a very desirable property. So, what is the space complexity of these two representations? So the first one, adjacency list, and the second one, adjacency matrix. Pardon me? N meaning the number of nodes? Okay, that's for... Right, right. How about the adjacency list? Yeah, okay. Let's see. So you're right. For adjacency list, we only store a list of the edges. So that will be O of V in terms of space. With the adjacency matrix, it will be O of V squared, and V is the number of nodes that we have of vertices. Okay, so right away we can see that it takes a lot of space to represent graphs using adjacency matrix. So which one is better? Again, we have to align the data structure that we use to the data and the application that we have in mind. So it doesn't mean that adjacency matrix is always better or adjacency list is always better. No, that depends on the application. Okay. So it would be nice if we had a way to basically combine the good things about both of these representations and kind of have a compromise between the two. And then enters sparse matrices. Let's see what sparse matrices are. So before that, I think it might be a good idea to take the break here, and then let's be back in 5 minutes. right, we're back. So let's talk about why it's important to have an alternative representation here called a sparse matrix. So the thing is, for real-world applications of graphs, what happens is that we usually do not have a fully connected graph. We usually don't deal with complete graphs or anything even near that. And this is, again, a recurring theme for a lot of other matrices that that we happen to work with in modeling and simulation and a lot of other types of mathematical computations. So the matrices are not just like full of values. We usually have very large matrices that only have non-zero values, like a fraction of the total size, not everywhere. So we need to have a strategy to deal with this problem. If we just store a matrix that's full of zeros and only, let's say, 0.1% of the values are non-zero, that would be super inefficient, storing a lot of zeros just for no reason. Okay, so this is why there is this concept of sparse matrices. First of all, terminology alert. So in mathematics, a sparse matrix is a matrix that contains a lot of zeros. So it's like a two-dimensional matrix. I mean, this is not related to code or Python program, anything. This is just a math idea. If a matrix has a lot of zeros in it, that would be a sparse matrix in mathematics. In coding, this sparse matrix thing is a particular data structure. Okay, so this can be confusing, but this is just a heads up here. All right. So just note that, yeah, it's possible to use a sparse matrix data structure when your matrix is not sparse, right? Because you can represent a regular matrix using sparse matrix data structure. It's possible to use a dense matrix data structure when your matrix is sparse. There is this two-way connection. Could be confusing at times, but there's just a heads up here. Okay, let's get into that. So there's our graph of looking like a ladder. And let's take a look at its adjacency matrix. Okay, so it says that this object is an adjacency matrix, right? And if we print it, it says that it is a sparse matrix of type class numpy int64, and it's stored in compressed sparse row format. Okay. Let's see. Yeah, okay, so this is basically the same output here. So you can see that this adjacency matrix is internally represented using a sparse matrix, not as a numpy 2D matrix. We can see that by checking out the type of it. Okay, so that's the default way. All right. And this representation is possible by using a package called SciPy, which is used for scientific computations in Python. So it basically contains anything that you want to do, like with anything in numerical methods, basically. A lot of linear algebra stuff, a lot of even statistics, differentiation, integration. Yeah, a lot of things like that. And sparse matrices are a particular type of object that SciPy has an interface for and a functionality for. All right. So one thing that we can do is that we can take a sparse matrix and do .toArray, and that will convert it to a regular array, numpy array that we are used to. Okay, and as soon as we do that, then basically the sparse matrix unfolds and unravels, and it takes up a lot of space again. Okay, so we have to be careful about running this command. And if you check out the type, you can see numpy n-dimensional array. Okay, and again, AM ladder is still a sparse matrix. Okay, let's make a bigger graph here. 100,000 nodes. Okay, we have this many nodes, and it's randomly connected. Okay, we have 500,000 edges, so an average of 5 edges per node. Okay, and if I check out the adjacency matrix, yes, it's of type SciPy.sparse. Check out the shape. Note that although it's represented as a sparse matrix, the shape, when we inspect that, the shape is what we expect it to be, so a two-dimensional matrix. And there's this function called NNZ, number of non-zeros, and if you run that, it quickly tells you, for example, here, you have about 1 million non-zero values. Okay, so there's a computation we can do here. The matrix was 100,000 by 100,000, which would have 10 to 10 elements. That's a lot of elements. And we only have 1 million non-zero items. If you divide the two, that's 0.01% of non-zero values. So this matrix is very, very sparse. And you want to see how bad would it be to store this as a NumPy array. So if we store it in full form, yeah, it takes 80 gigabytes. Yeah, so you can shut down the computer, go home, because we can't deal with these graphs of this type, even with just 500,000 edges. That's nothing. Okay. So, however, in this representation, it only takes up 12 megabytes. And that's about 10,000 times smaller. So we can immediately see that, okay, as soon as we scale up, it doesn't make any sense to use an adjacency matrix to do any kind of computation, any kind of reasonable computation. We already had the break. Okay, so any questions about the numbers that I've just shown you? Okay, well, we're going to go into a little bit more detail about the specifics about the representation, but just about what we have covered so far. Yes. Oh, that's because we don't store all of the zeros in that case. Yeah, so we only store non-zero values, and that would be much more efficient, basically. Yes. Yeah, if you actually, okay, so if you have a complete graph and you use that, so you have to keep track of more things, and then in that case it would be just not a good idea to use a sparse matrix. We don't, basically. We just keep track of the non-zero values, and then the way that that is interpreted by, for example, SciPy, it understands where the zeros are. Okay, so wherever we have a value, we have a value. Otherwise, it just fills it with 0 when you do the conversion between a sparse matrix to a NumPy array, for example. Yeah, so I'll have a visualization later on that will make this a little bit more clear. I'm not sure if that exactly answers your question, but we'll have a quick look at that later. Yeah. Okay. Okay, so now let's say we have this matrix, sparse matrix AM, which was defined here. Yeah, right here. No. Oh yeah. Here, okay. And now I'm just going to look at the first row, the first node here. So it tells me that the first node is connected to this node. It's also connected to this node. And these are the values that we expect for those connections. So if this was a weighted graph, we would see different numbers here, but this one just shows that there is a connection there. So you can kind of see how this particular thing is represented inside of our computer. So it's a tuple that basically contains the location of that particular value, and then the value. Okay. So this is a particular type of representing a sparse matrix. There are various ways that you can represent a sparse matrix. This is called the, I think, coordination format, something like that. So it just stores the coordinations of non-zero values and then the values. Okay, so there's some notational nuisances, and I'm going to quickly talk about them. So if you have just a regular NumPy array, there are two ways that you can return the values stored in particular indexes. So for example, at 1 and 2, we can do this. We can also do this. Okay, both of these notations work. Okay, and this is the reason is that x of 1 returns the second row, and then this 2 indexes into that row and grabs the third item, so it works. It is something like the pandas thing that we discussed in 5.11. So when you do something like this, Python first computes this part, returns it, and then indexes into that again. Okay. In this case, it doesn't do that. Okay, but it works out nicely with NumPy. All right, let's skip this. However, with sparse matrices, okay, if we do something like this, that works. If we do something like that, it won't. And the reason is because the type of object that is returned here is actually something like this. Okay, so it returns to us a row which contains 10 elements. Okay, and it is still a two-dimensional matrix, 1 by 10. Okay, meaning that we have only one row and 10 columns. And in that case, as soon as I do something like that, then it doesn't understand it because it's going to look for the third row, and there is no third row. So you have to be careful not to do that. This is just, again, word of caution. If it doesn't work, that's because the representation of what we get from single indexes is different compared to NumPy. So bottom line, always use this notation, this way of retrieving values. Okay. So dimensions separated by commas. All right. Yeah, so this is just, again, an indication of the shape of the row that's returned. However, with the NumPy array, the thing that we get back actually is a vector, has only one dimension. Okay. Okay, so there's the opposite thing that goes on with lists. So if you have a list like this, okay, this obviously works because this grabs the first element inside of that list, and that first element is by itself a list, so this one works. Okay. However, Python does not have any idea about indexing into a list like that. Okay. So with a list, again, we cannot use that particular notation. Okay. All right. So let's do some sparse matrix operations here. Random matrix initialized here, np.sum. Okay, that's the sum. And let's do the sum along the row direction, okay, along the column direction. Now, okay, back to this sparse matrix, and in order to find how many, for example, how many edges are connected to a particular node, we can run a code like this. So here, I'm getting the number of non-zero values along the column direction. So for each node that I have here, I go in this direction and count the number of non-zero values. That obviously gives me the number of edges connected to that. And then I can also see what is that particular node that has, for example, the maximum number of edges. So in this case, this particular vertex or node has 24 neighbors. That's the largest number of neighbors connected to a node. Okay, so this is just to show you that these kinds of operations that we do in NumPy, so summing along an axis or taking the mean along an axis and then finding argmax or max, these all work for a sparse matrix as well. However, one thing that you should be, yeah. Oh, let me see. So yeah, this one is a NumPy array. The other one, which is the AM matrix, that one is a sparse matrix. So this was just to show, okay, this works for NumPy arrays, it also works for sparse matrices. Yeah, and one thing that you have to be careful about to not incur additional cost is that when you have sparse matrix and you want to sum up the values inside of that sparse matrix, you shouldn't do something like np.sum. It works, but it converts that sparse matrix into a NumPy array, and that incurs additional cost. You should always use this .sum way of calling that method. Okay, because this .sum belongs to the SciPy function. Okay. So this is just going back to that thing that I discussed in the beginning, that real-world data sets that are represented using graphs are usually sparse. And again, that example that I told you, like 3D point clouds, if we represent them using a three-dimensional matrix, that we would have a lot of zeros. So if you represent, for example, this chair in a three-dimensional space of points, then we would have a lot of zeros. And then we will learn in a later course, in your deep learning course, then we will do a specific type of operation called convolution in neural networks. The cost of doing this over a 3D matrix is huge. It's almost not doable. So in that case, this is, again, an example of when we can use sparse matrices to represent that object and do our computations much more efficiently. Not just in terms of the computation itself, but also in terms of the space that we need in the computer's memory in order to achieve that. Okay. All right. And we can skip this. That's not important. Okay, so let's do some timing here with sparse matrices. Okay, let's 10,000. Okay, so a NumPy array with 10,000 elements, and let's sum the rows and columns here, and I'm going to explain what's happening. Okay, so here I'm summing the first row. Yeah, that's right. And here I'm summing the first column, and I briefly talked about this in DSCI 511. You can see that summing along the row is way faster than summing along the columns, although both have the same number of elements in them. And why? What is the reason, if you remember? Yeah, exactly. So these computers are much more sophisticated than we might think. So there is something going on under the hood called caching, meaning that when NumPy sends these values from the computer memory to the CPU, it actually doesn't send just one value at a time. It sends chunks of values to the CPU at each time. And because this matrix is stored in the memory in a row-wise manner, so it grabs this chunk of row, sends it to the CPU, so the CPU already has it ready to do the computation, and it doesn't take that much time. However, when you sum over the columns, then each time it has to grab this element, and then the next element in the column is stored way over there. So it has to go there and then come back here, and then because all of the values that have been cached, they're not of any use. So that's why. Okay. And summing the entire array takes 37 milliseconds, and that's about 5,000, 10,000. Okay, and that's about 0.37 microseconds, which is faster than even summing a row. Okay, so that's the average value per row, and you can see that summing the entire matrix gives you a better average value for summing each row. And again, this is because of some kind of optimization that is happening when you do a whole bunch of operations instead of doing one operation at a time over just one row. So instead of doing just one row, NumPy looks at the entire array and probably sends a lot of the data to the CPU instead of just computing this row and then going back again, computing that, going back again, computing the sum. Instead of doing that, it just does one whole giant big thing inside of the CPU. So again, on average, you can see that this per row takes less time than just summing one single row. Okay. Now let's look at the same thing with sparse matrices. So here I'm generating this sparse matrix with 10,000 nodes, right? 10,000. That's the number of edges. Okay, that's a graph. Now let's do the timing here. See what happens. Okay. All right, so again, you can see that summing along the rows takes much less time than summing along the columns. Why is that? This is now a sparse matrix. It's not a NumPy matrix anymore. Why does that happen? Any guesses? this should have something to do with the way that it's stored, right? The way that the graph is stored. And what do you think is the reason? Yeah, so the reason is that I'll show you later on about the type of the sparse matrix that we're using here, and it's called a compressed row format, meaning that it stores things row-wise, and when you do that operation by row, it just goes and look at that row, and then sums all of the values. Everything is right there inside of a nice package. However, if you want to do the same query on the columns, you have to go open each row, open the package for each row, and take the column and then add it to the one from the next row and for the next row, and that takes a lot more time. Okay, so again, there's the same notion here. You have to be careful about the way that you store your data. If there's an application that you know that the queries you're making will be working more on the rows, then you have to store it in a row-wise manner, whether it's a NumPy array or whether it's a sparse matrix, and vice versa. Okay. So what I was saying was this. So you can see here that it says this particular object is a SciPy sparse, and then CSR, which is compressed sparse row format, something like, yeah, it's mentioned here. Okay, let's see what we have here. So when you convert this sparse matrix to a NumPy array, this is the representation, a lot of zeros, all right? And now if I print X itself, you can see that this is the representation in the form of a sparse matrix here. And this is in the coordinates format. Okay, but the way that the data is actually stored is something like this. I found this graph on Stack Overflow. It represents the idea very nicely. So here you have the adjacency matrix, and these letters are the data that we have. So for example, they would be ones for an undirected graph or some other numbers for weighted graphs. And the way that it's represented is that, okay, we store the data itself, and then the indices of the columns where the data is stored, and then only one index for the row containing that particular value. And this is why we call it a compressed row format. We want to save some space for the values that happen to be inside of the same row. Okay. So going back to the question that was asked before, how SciPy knows where the zeros goes. So it starts filling up the spaces with the values that we have here with for those particular indexes, and anywhere else we know that we're going to have zeros. Okay. And these values are you can return them here using x.data. This is the data itself. These are the column indices. And this is called an index pointer, which keeps track of the row where that data is located. And again, this is a row-wise representation. You can have the same thing for a column representation. Again, doing these operations will be much faster for the rows because of the way that the data is represented. Yes? Right. I don't think it will be. Yeah, I don't think it will be represented at all. Yeah, because we still have the row indexes. We still know where the existing values go, and anything other than that would be zero. So there would be a problem with that. Yeah, the way that the data is represented, yes. Yes, that's right. That's right. Yeah. Row 3. Wait. This one. So that's a node 3 that's connected to itself and also to node 4 and also to node 5. Yeah. Okay. Okay, wait. 1, 0, 3. That's row 1, that's row 3. I think that has to do with the number of elements that's stored for that range of indices. That's my guess, but I have to check that to be sure. Okay. Yeah, I think it makes sense. Yeah. Okay. So, the important takeaway point here is, again, to know the implication of using a particular data structure for doing those operations that we're interested in, compared to using another data structure, which is the whole theme of this course. Okay. And, okay, if we have a compressed row format, converting that to a column sparse compressed format is easy. So 2CSC does that. And now, if we run the timing experiment again, we would expect that the row operations should take much longer than column operations because we have changed the way that the data is represented, and that's actually the case. Okay. How long does it take to convert? Not sure. Not sure. Yeah, there's a lot of details to how these operations are done. That's not even mentioned in the, I think, in the documentation itself. It should be somewhere in the maybe technical papers that are published for SciPy. Yeah. Okay, so we have a bit of time. We can work on activity questions, or maybe if you have any questions about the quiz. Okay, let's talk maybe for 5 minutes, answering questions for 5 minutes about the quiz, and then, now, let's do the activities first, because it's still fresh in our minds. So, let's take a break for a minute or two, and then we'll work on the activity questions. That's right. Oh. Okay, true or false questions. So, first statement, for a graph with E edges, the adjacency matrix is an E by E matrix. False. Why false? Yes, exactly. Yeah, so the adjacency matrix is defined based on the nodes, not based on the edges. Okay, it's the adjacency list that contains the edges. Okay, adjacency matrices of graphs are always symmetric. False, and in what situation it would be asymmetric? A directed graph, right. Okay, adjacency matrices of graphs are always sparse. False, yeah. We can have a complete graph or something like that. Okay, the space complexity of storing an n by n sparse matrix is O(n) squared. That would be false, because if it was O(n) squared, then what was the point of doing that? Okay, so what? Yes. Oh. No, not at least in the context of this course, because that's the whole point of using the sparse matrix. Yes, yeah. Because it just, contradicts with its name if it's full of values. Okay, let's move on. Check this question. Okay, so this question over here, in the class we saw, we saw cases where the sparse matrix representation was much smaller. Yeah, we saw that one was 80 gigabytes, the other one was 12 megabytes. Is the sparse representation always, smaller for any matrix, or can it be equal or larger in some cases? That's a good question. Yeah, so think about it for a few seconds. Okay, so what's the verdict? Any thoughts? So let me give you a hint here. We're not talking about like time complexity of operations. We're talking about space complexity, the amount of space that it takes. So can we say that, like in the worst case, the sparse matrix is as big as the adjacency matrix? Would that be a true statement? No. Because, okay, remember that we had that coordinate format where we store the coordinates of each value and then the value itself. So in that case, we have to store some extra information about the coordinates. So that incurs some more cost. Yes, yeah, exactly. If we're dealing with the worst case, then it's not good to use a sparse matrix. I mean, we also have that other constraint of time complexity when you want to look up values and you have to go, for example, row by row to look for a column. Okay, let's see which one is more interesting. Okay, so this one. When implementing an algorithm on a graph, how would the average number of neighbors of each vertex influence your choice between using sparse or dense representation for the adjacency matrix? So in what situation would you use a sparse matrix? In what situation would you use the adjacency matrix itself? Based on the number of neighbors. Right. Again, it's just a variation on the questions that we have asked before. So if you have a large number of neighbors connected to each node on average, then we would use the adjacency matrix because of its more desirable time complexity behavior. However, if we have very few neighbors, then it makes sense to use the sparse matrix. Okay, let me see. So, okay, so what's the space complexity of an adjacency matrix stored as a dense matrix as a function of the number of vertices and the number of edges? I think we discussed this before, but just to as a reminder. Yes, it will be v squared because in general for a graph the space complexity is v plus e. If it's a complete graph, the worst case, e by itself would be v times v minus 1 over 2, and that would be a v squared complexity. Okay, according to the documentation, network X returns the adjacency matrix as a SciPy sparse matrix. What is the space complexity of this sparse adjacency matrix as a function of the number of vertices and the number of edges? Excellent, yes, it would be O of E. Again, like we saw, what we store is basically the nodes, and then for each node we store information about the edges, and that's what dominates the complexity. Okay, so we have a few minutes left. If you have any questions about, like a specific question about the material that's going to be on the quiz or anything else, feel free to ask your question. Maybe your question will be helpful to others too. Okay. No questions? All right, so that's going to be it for today's lecture, and I'm wishing you best of luck for the quiz. Don't worry about it. It's going to be fewer questions that I thought I was going to put on the quiz. Yeah, we have 7 questions right now. I was thinking of 8, but I don't want to stress you about the time constraint. So 7 questions, regular stuff that we have seen on the lectures and labs.